Okay, can you hear me even remotely?
Yeah.
Can you see the screen? The screen, can you see the screen of the tablet remotely?
Of the tablet, yes.
Yeah.
Okay, perfect, thank you. So guys, we are not going now to talk about the Fourier transform. That's the topic of this second part of this lesson. So we call it Fourier transform. So the Fourier transform. Has any one of you heard about it? Yes, apart from previously, have you studied it in high school, for example, on in physics or in math? Mm-hmm. Mm-hmm.
Thinking to start the work with that professor. So I have worked with the months. He will give me the topic and I study it a bit and then I explain on remotely. And now I got also the scholarship in Japan, but on the same time I got the scholarship.
Okay.
So I joined this one.
But it's good to have a refreshing. So first of all, it was invented by, you see the screen? Yeah, by Jean-Baptiste Fourier in the 19th century. Okay, so it's very old theory. We might say that this theory that any periodic function, you know, a periodic function could be represented as an infinite sum of sine and cosine functions. And cosine functions are also called Fourier series. So this transformation that you see here, actually, it's at the basis of the signal processing. So it's super important because we can have this kind of a transformation. We might use it in lots of different tasks. Okay. Imagine audio, we use Fourier. Imagine understanding the stability of a system, we use Fourier. Imagine of physics, quantum computing, quantum physics, we all have this kind of Fourier. Why? Now, let's talk about the, theoretical new page. Theoretical foundation. So the question, by the way, it was invented by Fourier for the heat problem. He was trying to model the heat function in some way, okay? So the problem that he had was given it should be a G, a complex signal, what is are present and in what proportions this is the key question, let's say the research question of Fourier time. And then we have the intuition. So imagine listening to a chord accordo, a chord of a piano. It is a combination of notes that we hear as a single sound. Chord, it's a combination of notes that we hear as a single sound. Imagine un accordo, a chord, all played all together. It seems a single sound, but the truth is that it's composed by lots of harmonics. Okay? What are harmonics? It is a superposition of individual frequencies correspond to each note. So it's a superposition of different frequencies. Every frequency, it's, let's say, a note or part of an harmonic of a note. Okay? Let's say a note to keep it simple. Okay? So it's a superposition of individual frequencies. Una sovrapposizione, we would say in Italiano. Okay? So the Fourier transform extract these individual frequencies from the sound, which is a complex signal. So the Fourier transform extract those frequencies from the complex signal sound. Okay. The sound in this case, right? Okay. So we are, in what domain we are? We are in the continuous domain, okay? For now, we will talk about the continuous Fourier transform, okay? CFT. So let che fai? F of t be continuous function. Clearly, t is the time. T is a time-varying signal, a continuous function in time. Okay, like a time series. The CFT converts from f to f of omega. Oh, God. Okay, so we go from the time domain to the frequency domain. Okay, are you with me? We do so. Here we come. That's it. This is in the Eulerian form. We can break it down into. So, how this? What is this? So, is the frequency domain representation. This is the frequency domain representation of the signal of the signal. Oh, hold on. Okay. We said that it's a sum of all the frequencies, but because we are in the continuous domain, that's our sum. Sum over all the frequencies. Okay, the integral, of course. This is the Eulerian format, which can be brought somewhere. Okay. This is instead the Eulerian format, which can be decomposed as E. No. Let's change color. E to the I omega t is equal to cosine of omega t minus I sine omega t. Allows us to write the previous equation. Okay. We go here. Oh. You with me? We can break it down into parts. The first, let me change the color. Of omega of real part. is, guess what? Right? And then we have the f of omega of the, we call it imag, because we are in the complex domain, recall. No, I'm not sure. No. Right. So at the end, f of omega is f of r, the real, plus j f I, imaginary, of omega. Right? They're not seeing the magic here. This is magic. It's just magic. No? We'll get to it. Of course, this can be reverted, so we can compute the pre-image of this stuff by doing something that's called the inverse Fourier transform. I won't go into the details of the inverse, but by the way, that's it. So FDT, we are reconstructing the original signal, is 1 over 2 P of this integral sum here. So too far. Right? We are integrated over the frequencies practically to get back to the signal. And 1 over 2 pi Greco because it's a circular, right? Then we have, and we will see it programmatically, so from the code perspective, the discrete Fourier transform. Now, because we are in a discrete domain, I mean, as a computer scientist, we're not the continuous domain. We are discrete people, okay? So we work in the discrete domain. We have just to substitute the integral with a sum. And that's it. It's called DFT, or discrete. No, discrete Fourier transform. Right? That's called DFT. In Illyrian form, it's let's say a little bit easy to. Okay, that's it. It's x at the end times the e at the minus I to P greco Kn on the total number for K that changed from 0 to N minus 1. Here, X of key, this is a X, by the way, we will get in part. This is just to explain things. Is the amount of amplitude and phase of the frequency component at index K. This is the, ok, mamma mia, so più scrivere. Is the complex, scusate, sorry. It's the complex exponential of the kth frequency component. So we're analyzing here one frequency at a time. Which is sampled at an interval, so we cannot take on the full signal. It's the frequency on that time interval. And the time interval is, what is the time interval in this equation? It's of course n. Are you with me? Following. Yes, we can compute the inverse, but I'm not with this stuff. What are the properties of the Fourier transform? We have several properties. One is linearity. So f of a f of t b of g of t is equal to af of omega plus b f g, that was g, not f, plus b times okay. Linearity. Another property is time shifting. So linearity means that even if we scale or add something, we add them at the transform. That's it. Think. if we shift the function by a time, let's say f is t minus t with 0, its transform is shifted. Right? Instead of putting t, is t0. Okay, so we maintain the shifting. So the shift in time introduce what? A shift in phase. Okay. I suppose you know what's a sine and cosine and all the phase. Let's study it. We can also perform frequency shifting. I can write it here. Frequency shifting. And so we have f of t times e I omega 0 t shift the Fourier transform by a quantity, which is just omega. But now we have the most important property. Are you ready? It's called convolution. The genius of Fourier, exactly, said that the convolution of f of t, this should be the convolution operator, convolved with g of t is the product and for product I mean the pointwise multi of their transform. Mathematically, okay. Let's see, once transformed, so on one side we have the convolution, on the other side we have the pointwise multiplication. Why are not you jumping on the chair? Are you not looking at the beauty of this stuff? From the perspective, this is not a question for the math people, but from computer scientist perspective, answer me. What's the difference? what's the computation requirement of a convolution? At least. And what's the computation requirement of computing a Fourier transform? The FFT, Fast Fourier Transform, is n log n. What does it mean? It means that in the frequency domain, we can compute the, let's say, the convolution, the transformed convolution, in a fraction of time. So what can we do with that? Probably I don't need any more to go to see the code now. I have lots of stuff, but let's see the code. Did you see the beauty of this? Questions, even remotely, on this stuff? We know that to compute the Fourier transform, we might use the algorithm. The Cooley-Tucker algorithm is n has a complexity of n log n. And instead, the best algorithm, convolutional algorithm, has a complexity of n squared. That's much more less. Because it's, let's say, it's not linear, the graph, but it's not much more than a linear graph. It's a linear times a logarithm. Instead, the n squared is quadratic graph of complexity. Then we use it. And instead of using convolutional network, use something like Fourier neural. So get rid of the convolution at all. Are you ready to see it? Okay, up to now, any question? Even remotely? Okay. If we don't have any question, we move to the code. Oh, no. 1 second. Okay. Can you see the screen? Okay.
Yes.
So in this code, I have to upload some data. Let me record this stuff. Non read it. Qui forse. I have to upload this data. Connect, audio sample. We bring it here. Okay. This is called Colab. I think many of you know this platform. This platform allows you to write Python code and deep learning code and run it on the Google servers. Okay, this is the Cooley-Tucker algorithm for the FFT. You see, it's not.
Yes.
It does not iterate. Okay, thanks. It does not iterate. Okay, so it's an algorithm. It's a recursive algorithm, so it calls several times itself, always on more simplified data, let's say. So here we split. If we reach the base case of this recursive algorithm, we return the signal, which is our input, if n is equal to 1. If the length of the signal is 1, then we return itself. Then we continue. We divide the signal in two parts, even and odd. Pari dispari. Then we compute this exponential. Oh, you see, it was the E up to, okay, parts. Voice is going. Then we transform this n into a complex number. So we create a matrix that contains results, which has number of zeros equal to n, but it's of type complex. And then we add to the right part even plus the twiddle times odd, and to the left part even minus twiddle times odd. Transform. This is computed in log n log n time. Okay. Here we have the signal, and we can print it. Okay, error. This was the previous discrete Fourier transform that I've substituted with the FFT, but the DFT was just right, and the DFT is the practical implementation of what you have seen previously. But this is okay. This is just a shape mismatch, but this is the idea behind the Cooley-Tucker algorithm. Okay, this instead is the implementation of the Fourier formula by hand, right? Of course, this works. And here we can see the spectrum on time. On the right, the spectrum of frequencies. There are certain frequencies, like a frequency at 5 hertz and 20 hertz, which have a strong energy. Then we have this audio. It's not a music, it's an audio. Then there is the DFT here, and we generate all the plot for making the spectrogram of that. As you may see, it takes a lot of time to do. There are, let's say, things that are computed, that are library with the FFT at the processor level, which we call DSP, digital signal processing level. We are making it computationally, so we have to wait. But let's wait. Up to now, question? No, not
asking why so much time for a so short audio.
because it's not optimized.
Uh,
Because it's doing, where is it? It's here. It's still computing. We are, this audio at high resolution. So it's iterating over all the frequencies. This can be done by, for example, in electronics, there are certain circuits like FPGA that are made to solve this kind of problem. In your phone, when you do something like make a phone call with, let's say, with WhatsApp, or looking at an image on your phone, or an image, because JPEG, the information within the JPEG is just the FFT. And then when you see the image, it's the inverse FFT that is being built. Okay, that's why we save lots of information, because we take only the and central frequencies, and then we rebuild the full image with the inverse. So it takes a lot because we are iterating over all the frequencies. Instead, there are certain circuits that do that in hardware. Okay. And here we are, our spectrogram. But I said, can we get rid of convolution with properties of the pointwise multiplication? Yes, we can. Okay, let's read this. We know what are convolutional neural networks. These are the convolution. This is the convolution operator. We saw it in the previous lessons. Now, the theorem of Fourier transform, we convolution to the pointwise multiplication in the frequency domain. Right? Right. Good. Theoretical benefits. Okay, we go from odd n squared to odd n log n. It becomes more interesting as the kernel size increases, and it becomes much more interesting when the receptive field increases. What does it mean? If we have very big images, this technique is better than convolutional network. Now, because I told you to be suspicious like mice, this is our very trivial deep neural network. It contains a two-dimensional convolutional layer with 32 filters and a kernel size of 5. Then it's followed by a max pooling layer, flattened, and dense, 10 neurons in output with a softmax activation, because we are predicting the MNIST dataset, which contains the numbers and written numbers. Okay, so we have 10 numbers, and so 10 output. You with me? Then this is written in Keras with the TensorFlow, model fit, 2 epochs, and so on. We run it. Let's see if it works. The first validation accuracy is very high, 98.01% of accuracy. So up to now, nothing new. Now imagine to have this kind of FFT convolutional layer. So we have a tensor X which has the dimension of batch size, input height, input width, and input channels. And the kernel tensor K has the dimension of kernel height, kernel width, filters. Then we have the Fourier transform of the input and of the kernel. So we, apart from the zero padding that created really lots of problem, I wasted a lot of time in this padding and reshaping the kind of tensors. But the intuition is very trivial. Given a kernel, we compute the Fourier transform, and we have this x with the hat. Sorry, given the input, we compute this Fourier transform. We have this x with the hat. Given the kernel, we do the same. We compute the k with the hat. Then, instead of doing the convolution, we do this pointwise multiplication that you see here. Okay? And because we have this mathematical tool, we can put the inverse FFT, which is our output from this convolution, and then we feed it to the next layer. Are you with me? No. Hey, it's more simple than what you are thinking. We have an image. We have a kernel. Instead of doing the convolution, I compute the Fourier of the image, the Fourier of the multiplication pointwise, inverse Fourier transform. That's it. With me? Then cropping and bias addition just because we have to make the shapes work. And that's the code. You got the idea, right? Then I had to do some kind of transformation because working in the complex domain is not that easy. So we sometimes have to discard the imaginary part only for the real part. Then we do the FFT of the input, the FFT bidimensional FFT of the kernel. Then we perform this kind of eigensum, which reduce the sum of the input channel. Then we perform the inverse. This is also the product, it's here, okay? But done in this way is not easily understandable because you're not looking at the fact that it's doing the sum over the channels and then the multiplication. And then we perform the inverse. We get only the real part. We discard the part. And that's it. We have the bias, but more, that's it. That's the layer. This is the exactly equal to the previous architecture. The input, the FFT convolution, the new FFT convolution in place of the two-dimensional convolution, activation, max pooling, flatten, and dense. Compile, fit, 2 epochs, same. Let's see if it works. We got 98.01 previously. 98.20. Woo! FFT is better than convolution. So in let's look at the seconds for computing. Here we have 8 seconds for the first epoch, 3 seconds, 1 second. Here where are we? Here we have 8 seconds for the first, 6 seconds and 1 second. What's happening? The point is that here we are doing with the operator. Instead, the convolution, even if it takes the same time, 8 seconds, you have to see the first epoch. Even if it's equal, we have a very different implementation. Here we implemented all this kind of magic trick with several steps. Instead, the convolution operator, it's implemented in the video card by doing it in low-level language. So it's very close to the machine language. So to say in few words, the two-dimensional convolution is much more optimized than the code that I've written. Okay, so the system is losing lots of time in reshaping things. Okay, but just the fact that we get the same results in terms of time with respect to something that's extremely optimized, and so CUDA, which are the libraries for the computation of convolutions in NVIDIA GPUs, it's super optimized. Instead, my code is not super optimized. You get the same. Just think about it. Apart from the fact that we get the 20% more in accuracy. No, 20, sorry, 0.20. Slightly, but interesting. Question to see if you have understood up to now. What's capturing the FFT that the convolution is not capturing? Huh? No, we image space. Unfortunately, we didn't do the principal component analysis, but I assume that you know what a PCA is, right? You studied PCA. Then you have to do in maths. The master degree of maths. But you studied PCA, the principal component analysis, the singular value decomposition, you did it. Now imagine the SVD on a covariance matrix, that's PCA. The truncate SVD, explained in a few words. Okay, what's doing the Fourier transform here? It's capturing the principal frequencies in the image. So it's like a global operator. It's like a global attention mechanism. Okay. What if FFT is all we needed? Using FFT to replace the attention mechanism, the multi-headed attention in transformer models. Really? Huh? Huh? Good. This is good. There is nothing more left. Okay, background transformer, we saw it. Okay, query all these equation, Vasvani, good. Our friend has a quadratic complexity. And we hate this kind of quadratic complexity. By the way, I suggest you to read the flash attention paper, which is a technique used in large language models. But this is better. So the fast Fourier transform offers an efficient way to compute the operation involving convolution and correlation with on the n of log n complexity. So using FFT, we can potentially design models that capture global dependencies more efficiently than standard attention mechanisms. That's it. Linear complexity. The Fourier-based methods can reduce the computational complexity from quadratics to near linear log n with respect to the sequence length and global context. Because with the can get only the most important frequencies, it captures the global information about the signal, which is beneficial for modeling long-range dependencies. This is our discrete Fourier transform that you have seen previously. This is our inverse discrete Fourier transform. How are we going to use the attention mechanism? So first, we transform the input sequence. We apply the FFT to the input sequence. And there is not this. This is one solution. There are other solutions. I want to probably, you may think when you go back home at other solution to apply this FFT. This is one solution. Okay, it's not the final solution. So we transform the input sequence by FFT to the input, and we obtain the frequency representation. Then we perform the computation, the multiplication in the frequency domain to capture the global dependency. And then we perform the inverse Fourier transform to get back to our pre-image. And continues with all the things. So we want a FFT layer that, given an input sequence, transforms it in its frequency domain. This is given by f with the f first equal to f dot the element wise multiplication with the learnable weight matrix. Okay. Then we do the inverse, and we get the output with the ReLU activation function. But do you see anything magic here? It's just the FFT. Then we multiply it with a weight. Then we perform the inverse. And then we feed this inverse into an activation function. Is it easy? Nobody was. We have a reduced complexity of O d n log n. And we capture the global context, which is amazing. There are models. Okay, let's go. Then we are going to implement the multiheaded attention with this. Okay, parts that are always almost the same. And here you see also a few papers, really a few papers that are all 2021, 2020, 2024 that use this stuff. So it's very, very actual. Now, let's go to the FFT self-attention layer. So we have this projection dimension, which we know. Embed the dimension divided on the number of heads. We are re-implementing the multi-head attention with FFT, technically. Okay. So we have the query key and value, but they are fed inside a dense layer. So we have query dense, key dense, and value dense. If you remember what we did, the whole lesson on multi-head attention, you will see. Okay, a little bit of padding, FFT computation of the query is padded and the key is padded. Then we perform the attention as a point-wise, element-wise multiplication between the keys and the queries. And here is the magic. This was a dot product. In the multi-headed attention, this was a vectorial product. Instead, here, it's just point-wise multiplication. Inverse, and you get just the real part. Easy. Let's see the implementation. The implementation is not that trivial. Yeah, it's trivial. We have in this code two different implementations, the FFT self-attention and the multi-headed attention by Vasbani, just to compare them. You know, we select the same code, we shift from the FFT attention to the multi-headed attention to see the performance change and improvement change. Okay, the code is, this is the transformer block, which is exactly the same. It's a very simple BERT. like a encoder only transformer, which has depending on the attention type, we may use the multi-headed attention or the FFT self-attention. Then it has a dense layer, layer normalization, another embedding. The layer normalization, dropout, and then the final classification. Okay. This is the transformer block. So we are just changing the kind of attention. Instead of multi-headed attention, the FFT. That's the multi-headed attention implemented with element-wise multiplication instead of a vectorial product. Okay. We build the transformer. At the end of the transformer, we put, global average pooling. Work. I mean, to make things work means to allow the shapes to be compatible. Drop out dense layer for the activation. The problem is the IMDb database. So I want to classify if the movie that we are looking is the rating of the movie. It's a classification problem. And we're going to make it with multi-headed attention or FFT. Let's see if it works. It's downloading the IMDb dataset. Embedding dimension is not defined. Good. Where is it? Because this is called this is called by okay. Vocab sites. Okay, I'm missing here specifications of this thing. All right. Embed dim is equal to 64. Okay. It suggests to num heads 4 FFT. Okay, let's take the suggestion. Meh. Woo. Something is working. Let's see the multi-headed attention for time 5 epochs. It's training, guys. Oh, I love to see all the training, the stuff that goes. Let's see. Accuracy is 86, 87. 87 and 52. 5 iterations. 5 epochs. What do you want? 86. Let's see. Of course, here it's a very simple. We didn't prove any, technique for learning rate. It's okay. Started the FFT. So there is no regularization technique applied, and the network is very simple. That was I was trying to say. Okay, the first epoch went better. The second epoch went not as the second here, but that's that. Let's go. Okay, that's. I mean, I don't know why it did only 3 epochs here. Come on, no, perché only 3 epochs? Non lo so. By the way, do you see any difference apart from the the accuracy, but this was trained for 5 epochs, this only for 3. I don't know why. But do you see any difference? Oh, raga, I put it. Look at here. You have 10 seconds. 5. This is optimized. This is not. Qui è il primo 22, quello è il 20. Fai la somma. Make the mean. Take the mean. It's always better, even if it's not optimized. Now, these are very small network. Training ChatGPT with this thing with 175 billion parameters. Fourier is back. Fourier is all you need. Okay, this lesson is finished. Questions? All clear? Even remotely, do you have any question? Anything more to show you?
No, it's okay.
It's okay. Thanks. Okay, so the lesson of today finishes here. The next lesson, I don't know when it is. Monday, okay. Bring for who comes physically, bring your PC because you will read collecting the papers or ask me what paper and start reading the paper or doing the project, whatever you want. Okay, so I said you can or create a project where you do your experiments, or you select a paper and you present the paper. Okay, showing what you liked about the paper, what you did not like, and it can be improved. Okay, the paper, I expect some technical paper.
And
That's it. So
when is
yes.
the last lesson?
The last lesson when you will present is the 22nd, right?
22nd, yeah. Okay.
The 32nd, yes.
It's okay. Thanks.
Okay. Thank you so much. And last time for today. Any question?
Oh, thank you.
You want the implementation? For what? For the FFT?
Yeah.
No, you ask me. No, really. I don't know if there is this implementation line. Probably there is someone that made, but it's not equal to this because it's was for me just training you how to substitute. So it's just the multi-headed attention, instead of implementing it with the vectorial multiplication with the pointwise multiplication within the FFT. You have several changes implementation also for improving the performances and also for improving the stability and also for improving the time. But this was the trivial one to explain you that research is not something that we see, because Basbani said that the multi-headed attention works. We have to keep it and say, okay, we can always. And always another important factor is to get back to the theories. Study the theories. Okay.
Goodbye.
See you. Amsalu, also remember, and Feliciano, Vito, remember to sign the paper that, I mean, the sheet that I know. Yes, I will now upload. Okay?
Okay.
Yes.
Thank you.
You too.
Bye.
Bye.